We are here to share a little bit about your case that we applied Movile, and we use a simple solution of machine learning to solve a big problem for us. Especially, it's a problem that everyone here will face it someday. It's revenue. So that's it. And first of all, let me introduce myself. My name is Flavio Clesio. I'm the head of core machine learning team at Movile, and I hold a master's degree in production engineering, especially in computational intelligence. And the last year, I was invited to speak at the Strata conference in Singapore.
Okay, my name is Eiti. I'm IT coordinator at Movile. I'm working a lot with Apache Cassandra community, and I've been working almost 10 years with software architecture and distributed systems. So, all right, let's introduce our company.
Okay, I don't know if you guys know, but Movile, it's a holding, technology holding of Brazil. We are leading at services of sending content by SMS through apps. And this is one of some of our apps like Play Kids. It's a educational app for kids. I strongly recommend you guys to download to your nephews, kids, and so on. And the iFood, it's the leading delivery food here in Brazil through apps and so on. And the main vision of the Movile it's to be the company behind the apps that make your lives easier. Okay. But this is your agenda. This is we will discuss a little bit about. We are talking a little bit about your platform, and we'll show some demonstration using Scala. I don't know if you guys know Scala, but it's not such a difficult thing. And we'll discuss a little bit about the results and conclusions. The billing platform of the Movile, it's the heart of the revenue that we have. So in this platform, we perform some management over subscription services and billing. And when I say subscription service, I say weather report or financial information that you can receive in your cell phone, token, and so on through SMS or through apps. So if any kind of problem of outrage occur in your platform, we can lose a huge amount of money because your platform works 24 hours per year, 7 days per week, and any kind of outrage, we can suffer a huge loss of money. And to see some kind of dimension of these losses, this is the timely of the unavailability can cost for us. So with this kind of problem, we need to solve this with a more elegant way than to make manually query or data science like some kind of analysis made some by a human being. And we'll discuss a little bit about your problem of monitoring.
All right. So as you notice, we are responsible for producing some great mobile app applications. All right. So, but here in this case, in particular case, we're not talking about our mobile applications. We're talking about our back-end applications because we know that there are great applications behind in back-end to support mobile applications. So in this case, we are losing money on each hour that this application is down or we are suffering any problem. So this is why the monitoring is a big challenge for us. We're talking about a critical application responsible for the company's revenue. We're talking about distributed systems with lots of services spread along a lot of services running together. So this is not an easy task. It's not an easy task to understand because it's not a simple monitoring if your application is running or not, but if it's producing the right results we are expecting, which means to charge people in carriers, mobile carriers. When I say mobile carriers, we have here in Brazil so Vivo, Claro, Oi, and so on. For the people abroad, mobile carriers are something like Verizon, T-Mobile, Telefonica, and this kind of company, okay? All right, let's see the volume of data we have in our hands. We basically are performing about 230 billion attempts on those carriers today. Here in Brazil, we have 4 main mobile carriers. which drives all of our operation. And before our solution we're proposing here, we used to analyze data manually. All right, we have this table in our hands. We have the data consolidated here by the carrier weight, which identifies our carrier, and consolidated by day and hour. So I can compare the results I have in my hands with the previous days and check if I have any discrepancy in the numbers. There's a problem, we have to take actions. Basically, we have some properties, some features regarding to the carrier service, like average response time, for example. We analyze the total attempts, the last column of the table, which represents the attempts of billion attempts I'm performing against the service of the carriers, and the success charges. Those values are not in currency value, it's a unitary value, all right? But we used to analyze this table like this, frequently during the day, but it's a pretty manual, right? We think about some intelligent way to solve this kind of thing. That's what we're going to present here today. Okay, regarding to machine learning modeling problem, we have the same attributes of the table in the previous slide. We have the data I'm trying to predict here, is most important for us, which is the number of success. We have the label, we have the data we're trying to predict, and we have a set of features related to that data, like carrier, hour of the day, so week of the month, and so on, and the other attributes. Well, I know what I'm trying to predict. As I know the label, we have a category of machine learning problem as known as supervised learning. And the value I'm trying to predict is not a categorical value. It's not a problem of classification. It's a continuous value stat, but it's regarding to a linear regression problem. This is what we have in our hands in terms of machine learning to work with and to solve. To work with this kind of thing, we're using Apache Spark, which is a general distributed computer platform, which has a bunch of libraries known as Apache Spark MLlib, responsible to do machine learning in scale.
How many of you guys know Spark here? Okay, very good. It's very good.
So Apache Spark already provides us a lot of algorithms and models to test and use. So we have some simple linear regression model with stochastic gradient descent, plus the same algorithm with some regularization with like lasso and ridge regression. And the last one is a decision tree using linear regression. Okay, we tested all of them and checked the performance of each one.
Okay, and this is on-the-shelf algorithms that you guys can select in Spark MLlib. This is no transformations, not custom algorithm. At the moment you guys install Spark at your notebook or in your server, you guys can already have this kind of models, okay?
Great, this is our life cycle here. We have our data set. We are extracting our features from the data set, and the next step is to split our data set in two parts, basically. So the most of part of data to train our model, and some part to test our model. Then we'll train with model in our hands. We'll evaluate and score against the test data, that is the unseen data to the model, to see how it performs. This is basically what we do. Now let us show you in practice how to do this using Spark Notebook. Spark Notebook, all of code here is in Scala.
Everyone is seen? Everyone seen okay? No? More zoom? No? Okay.
All right. So you can do some data exploration, train models, and so on in your local machine using Spark Notebook. It's a very nice and interesting tool.
It's good.
All right. I'm running the pipeline that I showed in the previous slide, all right? So I have some imports here. Then I have two functions to extract the features from the data set. It's very, very simple, because I have a build label function to extract from the data set what I'm trying to predict, which is the number of successes in our case, and the build features, which will simply remove the data I'm trying to predict from the array, all right? Here I'm loading the data set. Which data set is this? Is exactly the same data I show in the table that we're analyzing. Instead of a human will start to analyze, I'm giving all of those data, those lines of that table to an automatic algorithm trying to learn over the data set. And I'm applying those functions here and returning a label point object. So label point data structure is required for Apache Spark to train machine learning models. The next step is to random split our data set. 70% of data sets used for training and 30% of data sets used for tests. Okay, this is an auxiliary function. Just we will print some metrics for the performance metrics of our model. It calculates the occurrence of the model, the mean square error, the root mean square error. And notice we're considering here that the model was able to predict when the error is lower than 20%. Okay, this function returns me the model training itself. We have the range. Those values are the carriers. We decide to create different models by carrier because each carrier has different behavior along the mouth. So that's why we have to filter in the data set by carrier here. And we're using some properties of the training. We have the impurity like variance, which means that this case is the decision tree, all right? It's a decision tree, but it's not it's a decision tree with linear regression. That's what means that variance, the purity. We have some other properties like the max depth of the tree and the number of the beans along the depth. Okay, this step we're filtering the data set by carrier, and we are calling decision tree.train regression. This part, effectively, the model will be trained. This function will return a map indexed by the carrier and returning me a model, all right? Okay, let's train the model. We'll just invoke the function that we defined in the cell above. Okay, with the model in our hands, it's time to evaluate and to see how well or not the model is able to predict our data. To do this, we are using here as one metric that matters for us. We are considering the root mean square error. It's a well-known metric to evaluate linear regression models. And now we are evaluating the model. Notice we are using here the test data set, all right? The unseen data for the model. We are getting the carrier, then we will use our map and get the model for the given carrier, and we call the model.predict. In this part, we will have this function return a tuple of data with the expected value and the predicted value. So this tuple will be informed to the print stats auxiliary function, which will compute the accuracy and the other metrics. As a result here, we have a model accuracy of 96%. We have the mean square error and the root mean square error very low value, all right? And after all, you can save it and persist your trained model to the disk. The advantage of using this kind of tool is that you can use, for example, here, we're using Scala to train our model, but you can load the trained model in any of the other languages supported by Apache Spark, which is Java, Scala, Python, and R. Okay.
Good. And train it with this on-the-shelf algorithms of the Spark MLlib. We get these results. And as you guys can see, decision tree model with regression properties shows the best result in terms of RMSE. And for this, we just recall some very old term of machine learning that if you have a simple model that shows accuracy more than 85%, I think it's better to put in production. And based on this, we thought, okay, let's put the solution inside the production and make the prediction. So let's remove any kind of manual creating over the data set, and let's put this in production. So think about that. We start to put the Watcher AI.
Yes, we decided to put in production, create a software called Watcher AI, which it was written in Java, all right, using the model trained with Scala and Apache Spark. Exactly the same way we show you here, all right. That notebook that creates a model and persists a model to the disk is the heart, is the core of the software. We are just loading up the model here. Let's show you some details of the architecture of this small software. All right, Watcher AI is basically a scheduler. It's running hourly and performing analysis. It loads up all of our training models for our carriers previously, and hourly it will get data to our analytic database and get the current status of the carrier in that particular hour and make some predictions. In case of discrepancy in any problem, we'll notify people using Pushable API, which is a third-party API.
It's like also?
Yeah, and another tool as well. We have our corporative chat. We're using Slack. We create a bot in Slack to be able to notify people directly in our corporative chat. And we can notify people using SMS as well. All right. So everybody will be notified and will know about a problem that it's running in that time.
Okay, and with this framework, we shortened the time for the troubleshooting, every troubleshoot of the platform, and let's see some results that we have. So this is most of major results that we have in the 1 year and a half when we started with Watcher AI. The first major result is we avoid to lose more than 3 million of US dollars in leakage because before, as I said before Watcher AI, someone opened the Beaver and made the query over the database and looked at the data. So okay, that's okay or that's not okay.
I feel it's okay.
Yeah, my feeling it's okay. My gut says it's okay. I have a faith that it's not happening here, but with Watcher AI, we eliminate this kind of thing. We saved more than 500 working hours because before Watcher AI, we have several alerts based on SQL queries of the data set, and even the seasonality, the threshold, it's up and down, and we have to recalibrate everything. It's a kind of massive thing, and the third major result is the recovery time drops from 6 hours to 1 hour. And Watcher AI reviews for us several problems that occur in your infrastructure and platforms and kind of bad deployment and so on. And before Watcher AI, we don't know what's happening in the platform, and with the solution, we have the complete diagnostic of what's going on in the platform. It's the response time, it's the number of attempts, it's the success, and so on. And before to make any kind of troubleshooting, we have the whole diagnostic that we need to solve the problem as quickly as you can, because every time that we are stopped or our platform is down, we are losing a huge cache. Okay.
All right, it was designed to be our last barrier of monitoring, but given the results, in fact, it's our main tool of monitoring of this platform right now. And it's just the beginning, right? We have lots to do to keep improving in our solution. We can basically think about, we are getting data hourly, right? Why not to store this data and use to refeed automatically the Watcher AI, for example. and then that can detect when maybe the performance is not going well and try to refeed and retrain the model. It will be a very nice thing to do. We have in our hands some details of our carriers we are integrating to, all right? So why not to create models able to detect problem with carrier? It's not an internal problem of the company. It's a carrier problem, a service failure, and something like that. And then we can notify people directly responsible to this kind of thing, or open a ticket to support on the carrier to try to fix the problem as soon as possible, and some kind of this. We're thinking about refactor the system. In fact, it's a job that is already in progress. We are rewriting all of the code with the new version of Spark. We are creating some kind of splitting the Watch AI, that architecture that I show you, splitting in two parts, like a more microservices approach, and with an API able to predict our values that we need, and another software to consult those values. And we are trying to do as well, it's still in progress, to create a more intelligent bot to interact to guide the software to do some kind of analysis for us in case of problem when a problem occurs, and something like that. So we have lots to do, and the message is don't limit your mind, all right? And I don't know if you get here, but the part what shines in this presentation, all right? We're not talking here about a very complex solution. We're not talking like some more complex, like deep learning and convolutional layers or something like that. We are talking here about a linear regression and a decision tree, which was able to solve us a complex problem for us and help us to save more than $3 million US dollars in 1.5 years. Okay, that's the part that brightens this presentation, is the simplicity of the solution. Okay.
Okay. Thank you everyone to come, and you guys can fork. This repository, it's open for everyone here. You can fork and put in your production system and can share and so on.
Yeah. You can download the notebook we show you here in this address of GitHub repository. You can download and reproduce the result we were showing here in your company, in your home, in less than half of an hour, right?
Okay, thank you guys. Thanks. Thank you very much.
Okay, thank you. Let's see if we have some questions. We have one here.
Hi. Do you have some special reason to use Scala on Spark?
We don't have any kind of preference, but when we started with Watch AI, we are using 1.6 Spark. I'm not sure. And at that version, the Scala, it's the only language that we can perform this kind of analysis. So we just continued it. But you can do this kind of model in PySpark and Spark Car and so on, and put your models in production.
Oh, hi. First of all, congratulations on the job. It's
thank you.
Very good done and explained it. And one thing that I didn't get it is how you use your predictions in production in real time, because you need the actual current values from the monitoring to predict the success charges. But when you predict, you will also have the actual current one. So you have the actual value and the predicted one. So how do you use them? Do you compare them? Do you have any kind of forecasting?
Yeah, we have our the current status of the platform are the current status of each one of our carriers. Are the numbers, the number of attempts, the number of success for that carrier at a given hour, for example. So use the software to predict which will be the number of success in that hour for that carrier. Then we read the current status of that carrier and check if the number of success are the same or are similar. So in case of a large error, right, in this discrepancy between those values, we will notify people because something is not right.
And we put some tricky here in this function, especially in this line, that we compare the results, and when we are dealing with the below threshold of the data, we put if the deviation is more than 20%, we sound the alert. If not, it not occurs. Okay, so we put this to avoid some kind of false alarms over the day. Okay.
Hi. So for what I understood, you guys run a bunch of batch jobs on Watcher AI every hour. Is it correct?
In fact, hourly, we're reading the data from our database to see the status of the platform, and we are making predictions hourly. Right?
Okay. But you guys have some tool to monitor these pipelines, like you get the data, run analysis, or you just use Spark DAGs, direct acyclic graphs?
No, we actually only use, we perform a simple query over the Amazon Redshift that you guys are used to. And we use summarized query with group by and so on, and over the Redshift and grab this data and compare with the model. So we made this hourly because the dynamics of the billing can fluctuate a lot inside an hour, and so this is why we choose the hourly fashion monitoring. Thanks.
Hi, I wanted to know, you say that you want to maybe change the model, right, to update the model to if the model is not right, or if there's some behavior that changes. But also I wanted to know, to do these predictions, how long your data, it's from a range of time, how much time do you take to make those predictions? Because, for example, in my case, it's sensitive to know how many data I have, how many historical data I have, in order to have good predictions, and how those behavior can change. The seasonality, if the season changes, how do you manage to infer that behavior?
It's a very good question because we have lots of data, right? We try to train with a large amount of data, like 6 months of data or 1 year of data, and it was very costly for us to do this kind of thing. But in fact, the accuracy was very poor, very terrible result, because we start to understand and study the nature of data, and we know that this kind of data is changing according to our product's configuration, and it's changing a lot along the time. So based on our experience and the frequency of the changes of the products in production, we decide to grab just 2 months of data to train our model. All right.
This is window of time we discover empirically because your businesses, it's very several factors that it can impact. It's unavailability of the carrier, the media that we invested to put more users, some kind of problem at the platform, and several exogenous factors that can